Serious vorticity.
Yeah.
Like that was leads to more interesting problems.
Okay, well, welcome once again to our Monday Colloquium. It's my pleasure to introduce Professor Chin Lee from our Department of Mathematics. Dr. Lee got her BS in Physics and Mathematics at Tsinghua University in China in 2009, and she went on to get a PhD in Applied Math in the Mathematics Department here on campus in 2013, working with Professor Shi Jin. She went to the California Institute of Technology for 2 years, where she was a von Karman instructor, and then returned to UW-Madison in 2015 as an assistant professor in mathematics, and recently was a recipient of an NSF Career Award, which is a high honor. And her general research interests lie in numerical analysis and scientific computing, and she'll be talking today about low-rank structure in forward and inverse kinetic theory as it pertains, I believe, to radiation.
Yes, I changed my title a little bit to attract my audience. I had a very fun visit and met with very interesting people and a very, very lovely conversation. I'd like to talk about low-rank structure in forward and inverse kinetic theory. So as you can see from the title, there are 3 themes. I'm going to introduce you what do I mean by kinetic theory and what do I mean by forward and inverse kinetic theory. The mathematical tools that I'm going to use is the low-rank structure in the system. So I'm going to explain how do I use that. So it's a collaborative work. In the forward setting, Ko Chen is my student. He's graduating this year, heading to Austin as a postdoc. Jeff Lu is my long-term collaborator from Duke. Steve Wright is optimizer on campus. In inverse setting, Ruiwen Shu is now a postdoc in Maryland. Wu Yulai and Li Wang, they are my academic sister, now tenure track professor in UMN, and Gunther Woman, he's a big promoter in inverse problem. So let's start. This picture is taken in this building. So over here, so what we do is we put this instrument in the outer field and we send photon to the sky. And by counting the photons that get sent back, we can predict how far up, how many clouds are accumulated up over there. So this is in time. So basically at this particular time, we see this much cloud up over here. And one intersection of this plotted over here, you can see in altitude, we have this much absorption coefficient and this much scattering coefficient in the radiative transfer equation. So the equation looks like this. F is a distribution function. It tells you the distribution of photon particles at particular time t, at particular space location x, moving in particular direction v. So there are 2 terms in this equation. So this is the time dynamics get governed by 2 terms, and this basically tells you my photon particles move with velocity v in x direction. And this is the scattering collision operator that tells me my photon particles get scattered around by the cloud. So the cloud information is basically encoded in this operator. It's a complicated integral operator. Let's ignore the detail for now. The second picture is taken in Caltech in Paul Balance lab. He's an applied physicist and he studies plasma. So he basically pumps plasma into this big tank, and then you watch the dynamics of plasma through this window. And if you ask him to write down the equation for plasma particles, this is the equation he gives you. The F, once again, is a distribution function. It tells you at particular time t, at particular location x, how many particles are moving with particular velocity v. So it's a distribution function on the phase space. So if you watch this equation, there are the time dynamics get governed by 3 terms. This term tells you my particles move in direction x with velocity v, and this term tells you my particle with velocity v get accelerated or decelerated by the electric field E. And the right-hand side is a complicated integral operator, and he uses the Fokker-Planck operator. It's complicated, let's ignore the details, but this equation tells you the dynamics of plasma particles. The third picture is taken outer space. So this picture is taken by Cassini. It's a spacecraft sent out by JPL. And when it was traveling in the universe, it takes pictures of all these planets. This planet is called Euclides. is number 6 moon of Saturn. And this area is the south pole of Euclides. And this plume is generated by water vapor. And if you ask aerospace people to write down the model for this water vapor, this is the equation that you get. We call it the Boltzmann equation. Once again, it's the same structure. F is a distribution function. It tells you at particular time t, at particular location x, how many particles are moving with particular velocity v. So it's once again a distribution function on the phase space. The dynamics is governed by two terms. Particles move with velocity v in x direction, and particles collide with each other according to the collision operator. So all this general structure, we call it the kinetic equation. Either the Fokker-Planck equation for plasma, or the Boltzmann equation for water vapor, or the radiative transfer equation for the photon particles. And you can imagine if you have a large number of particles and they follow the same physics laws, instead of tracing the trajectory of each particle, we want to describe the statistical behavior of the lump of particles. And over there, we need the distribution function. F tells you how many particles at certain time t, at certain location x, with some certain property v. It depends, t is always a time, x is always a space, and v depend on your particular particles you're looking at. Sometimes it's velocity, sometimes it's frequency, sometimes it's angle for photon, for example. And the equation always like this. The dynamics is governed by x dot equals to v and v dot equals to acceleration, and particles interact with each other. So the left-hand side, these two terms tells you the trajectory of the particle, and the right-hand side tells you how particles interact with each other. Some similar models are written down as the run and tumble model were used for modeling the dynamics of bacteria, and multi-agent systems were written down for simulating how human beings interact with each other for economic systems. And neutron transport equation almost look exactly the same as the radiative transfer equation. So they are all under the framework, we call it the kinetic theory. Okay. All right, so that's for kinetic theory. So what do I do for kinetic theory? For kinetic theory, I work on both the forward problem and inverse problem. And let me explain what do I mean by forward and inverse. So forward is straightforward. I write down this equation, and I tell you everything inside this equation. I tell you what is the electric field, and I tell you how particles interact with each other, collision operator. And I give you the initial condition. I tell you at time t how the distribution function look like, and I tell you the incoming boundary condition. I tell you at each at all the time how many particles are coming into the domain. So I give you the boundary condition, initial condition, and everything about this equation, and I solve this equation for the distribution function, for the solution of the equation. That's a forward problem. Inside this forward setting, we ask the following question. As a mathematician, we ask the following question. Is the equation well posed? In the sense that if we write down this equation, equip this equation with certain initial and boundary condition, does this equation truly have a solution? In what sense we have the solution? If you have the inflow boundary condition or spatula boundary condition or diffusive boundary condition, different boundary condition may give you different behavior of the solution. So what kind of boundary condition can we impose for a unique solution? We also ask a question about the limiting region, in the sense that the equation, the solution to this equation may look differently if you are looking for the long time behavior, for example. You ask your system to evolve for a very, very long time, and you ask, is my solution going to achieve some kind of equilibrium after this long time? And if that is the case, we put a small epsilon in front of partial t that eliminates this term, that basically gives you the steady state of the right-hand side. So you're looking for the equilibrium of the system. Or we ask about the strong field, in the sense that if your electric field is extremely strong, you accelerate your particles very, very quickly, then the solution to this equation might behave differently. What can we do when epsilon is small to enlarge this electric field? And the third regime is a strong collision regime, in the sense that collision operator is enlarged by epsilon. We divide this collision term by this epsilon when epsilon is strong, or when epsilon is small, this term is extremely big. That means particles collide with each other so often. What would that lead to when I watch the behavior of the solution? I should emphasize that, so in mass field, this metal called Fields metal is extremely important. You may have heard of it. Every 4 years we gave out 4 Fields medalists. During the past 30 years, there were 2 Fields medals given out to PDE, and both of them are for Boltzmann equation. The first one is to show that this equation indeed has a solution, and the second one studies the long-time behavior in the sense that when time goes to infinity, the solution has an equilibrium, and this equilibrium looks like a Gaussian. So intuitively, physicists already know the Boltzmann equation, of course, has a solution, and we go to equilibrium, but it takes a very, very long time for mathematicians to prove it. So I'm not claiming I'm at that level, but what I do is I look into the details of this analysis, and I ask, suppose you know the behavior of the solution. Can you compute this equation? This equation is hard to compute. If you think about this f depends on time, that's 1D. Space, that's 3D. Velocity, that's also 3D. So the distribution function lives on 7 dimensions, and you need to 6 dimensions, and you need to involve it in time. So the computation is extremely hard. So we ask the question, suppose we know the behavior of the solution in the sense that we know the distribution function is smooth in some region, so we can use force mesh, and stiff in some other regions, we have to use very, very dense mesh. Does such understanding help us to build fast solver? And that's my goal. So my goal in the forward setting is understand this equation and use this understanding to build fast numerical solver. In the inverse setting, I'd like to draw the analogy with linear algebra. Forward problem is more like, I gave you the equation, I tell you the matrix. I gave you the initial and boundary condition, I tell you x, and I map this equation to the solution in the sense that I multiply a matrix with the given x, and I find b. So that's a forward problem. I gave you a matrix, I gave you incoming data, and I find the solution. There are 2 kinds of inverse problem. One inverse problem is, I tell you the equation, that is A, I tell you the outgoing data, that is B, and I ask, what kind of initial data should I prepare to obtain that final data? So I basically need to invert this matrix A to find X. But that is not the inverse problem that I care. The inverse problem that I care is, I do not know the equation. So I write down this equation. I know the equation looks like this form, but there are many parameters in this equation that I don't know. For example, the electric field can be some random functions that I don't know. And how particles collide with each other, that is some functions that I don't know. I only know there exists this electric field, there exists this collision between particles. How can I recover this thing? And the information I get is the incoming to outgoing data pair. So basically, I have this tissue that needs to be reconstructed, and I send light in, I collect the light out, and use this incoming to outgoing light pairs to reconstruct my tissue property. And that's the inverse problem that I care. So I would like to utilize the collected X, the collected B, this XB pair, to reconstruct the information in matrix A. So over here, still several questions. Suppose I give you the initial condition. I tell you initially I prepare my solution looks like this, and at some certain time, final time t, I collect my distribution function. Can you use the initial and final solution to reconstruct the parameters in the equation? Or over here, I tell you the incoming light, or I collect the outgoing light. So this stands for the incoming light and outgoing light. I collect the incoming and outgoing light. Can I use this data pair to reconstruct the parameters in the equation? We ask a few questions like how many data pairs or how many incoming to outgoing data pairs I need to prepare or I have to measure to uniquely reconstruct the parameter inside. If you imagine, suppose I want to reconstruct my hand, I shine light in and collect the light out. How many this incoming to outgoing data pairs I have to collect to reconstruct my full hand? And how stable is that in the sense that if my perturbation, if my measurement gets perturbed by a little error, can I still uniquely or stably reconstruct my hand? So in some sense, we call it, mathematicians call it the well-posedness of the inverse problem. So in our case, for radiative transfer equation, for example, I gave you the incoming and outgoing light. Can you reconstruct the absorption and scattering coefficient in the right-hand side, in the collision operator? So lastly, low-rank structure. So a rank of a matrix is a well-defined concept. I gave you a matrix, and I tell you this matrix applied onto orthogonal vectors v1 to vn, it maps this v1 to vn to orthogonal vectors u1 to un. The only thing is u1 gets stretched by sigma 1, u2 gets stretched by sigma 2, etc. If at some certain k, I know that the rest of the stretching is very small, and I truncate it off, I approximate it by 0, then we call k is a k-rank approximation to the system. So the system is low rank if k is extremely small compared to the degrees of freedom m. So in the algebraical sense, I write my matrix as a singular value decomposition in the sense that I write my matrix as a product of a unitary matrix here and a unitary matrix here and a diagonal matrix over here. If only a small number of diagonals is big and most of the diagonal terms are negligible, we say the system is of low rank. The geometric interpretation is I have the n-dimensional, very large n-dimensional unit surface, and I map this matrix A onto this unit surface. It gets stretched into n-dimensional ellipsoid. If this ellipsoid has several dimensions that get stretched, and most of the dimensions get compressed, then we say the system is of low rank. So if a system is of low rank, you can imagine that basically means I have a unit sphere and I use this matrix A to map this unit sphere to a very skinny ellipsoid. That basically means lots of the dimension of the degrees of freedom can be thrown away. They are compressed, they are not eligible in my outcome. So the low rank structure in a system, that basically means you can throw away these degrees of freedom without causing any error. So now the question is, why do I say that kinetic equation has low rank structure? And why do they have, what is the low rank structure inside kinetic equation? And if I claim that kinetic equation does have low rank structure, how do I utilize this low rank structure in your equation? In a nutshell, I would like to argue the kinetic equation has low rank structure because somehow you can find its so-called fluid limit. And the fluid limit can be characterized by the so-called macroscopic quantities. And macroscopic quantities usually capture the key feature of your system, neglecting all the remainder noise. And if you know that your system can be compressed, can be uniquely represented by several features and throw away all the rest of the perturbation, then in the forward setting to advance the computation, you can simply say, let's just ignore all these details and only capture those features. So building this low rank structure into your forward computation, it can advance our computation. And in the inverse setting, you assume that your system has low rank structure. That basically means you start from different setups and you end up with the same measurement. That basically means it's very hard to invert from the different variation of your initial data. So the low rank structure, if your system is of low rank and you throw away a large number of degrees of freedom, the inverse problem is severely ill. Okay, let me explain them one after another. Why do I say kinetic equation has low rank structure? The answer lies in the fluid limit. So I'm trying to explain here how to characterize light propagation. There are two ways. The sun shines on the Earth. Some of the photons propagate through, and some of the photons get scattered around by the cloud. So there are two phenomena, propagating or the transporting and the collision. The F is the distribution function as we claimed before. It tells you at particular time t, at particular location x, how many photons are traveling with angle v. This dynamics is controlled by two terms, the transport term and the scattering term by the cloud. So that's one way to describe the propagation of light. Another way to describe the propagation of light was hinted 500 years ago by Da Vinci. He said, if you move an object 5 times away from you, this object looks 5 times bluer. So sometimes you get asked by the kids, why the sky is blue? The answer is the same. So in the entire spectrum of visible light, blue light is the light that diffuses the fastest. And when we're talking about diffusion, then the mathematical term for the diffusion is the diffusion equation. So now we have two different equations for one phenomena, light propagation. That's strange, and that puzzled Hilbert 100 years ago, and he said, the universe should be universal. If you have one physical phenomena, two different equations should be somehow equivalent to each other. And he asks, what is the intrinsic connection between this radiative transfer equation and this diffusion equation? So after this 100 years of hard study, we somehow know what is happening. So let me write down, this is a steady state radiative transfer equation. And I'm putting this number, we call it the Knudsen number, in front of the transport term. So this number has a physical meaning that basically means I have a photon, and I just collide with the media, and I start transporting. Before I get scattered again by the media, how long can I propagate? So this Knudsen number basically indicates how frequent you get scattered. When this Knudsen number is extremely small, that means your photon particles get scattered so often, and then somehow you achieve some kind of equilibrium on the macroscopic level. So over here I have two kinds of light sources. I have a laser light and I have a flashlight. The only difference between these two lights is the laser light is high energy photon and the flashlight is low energy photon. I turn these two light sources on, the laser light propagates right through, and the flashlight immediately shines up the entire room. The difference is the high energy photon, or the laser light, has high energy, so it barely scatters, but the flashlight, the energy is low and it scatters so often with the media. And when it scatters very, very often in the media, on the outer level, it looks like your system gets diffused out. So mathematically, we say, let's start with the radiative transfer equation, and we have this Knudsen number going to 0, indicating you scatter a lot. Now asymptotically, we build this structure called asymptotic expansion that basically says, if you do have a very small number in your equation, you can expand your solution in terms of this number. You have one function that is independent of this small number, and the second level is multiplied by this small number, and the third level is multiplied by this number squared, etc. And you put this asymptotic expansion back into your equation, and then write down some matching conditions. Somehow, in the end, you can prove that when Knudsen number goes to 0, this distribution function can be written as a multiplication of two functions. One function only on x, and one function only on v. The function on v can be uniquely, explicitly written down, and the function on x satisfies the diffusion equation. So that basically means when the Newton number goes to 0, you start from the radiative transfer equation and you converge to the heat equation. These two equations are indeed equivalent in the small Newton number region. And I call it the Lowrank approximation. So we start from the radiative transfer equation, and over here, our distribution function is a function of space x and velocity v. So if you plot it out, I have x direction, I have v direction. Every pixel has a different value. But you also know that when Newton number is diminishing, the radiative transfer equation becomes a heat equation, and heat equation only has a spatial dependence x. If you only have spatial dependence x, the velocity direction is universal. You only have the variation in one direction. So somehow the unknown, or the degrees of freedom, get compressed from 2D to 1D. And I call it the Lowrank approximation. The rho is a Lowrank approximation to your distribution function f. So that's what I mean by the kinetic equation has Lowrank structure, and the Lowrank structure is encoded in the fluid limit. And I should mention that the connection between radiative transfer equation and the heat equation is seen in many other systems as well. The problem that I mentioned that got 2 fields award is the Boltzmann equation. Boltzmann equation is proved to approximately equivalent to the Euler and Navier-Stokes equation. That's why the aerospace, the airplane design, when you design the aerofoil, sometimes people use the Euler equation as approximation, sometimes people use the Boltzmann equation as approximation. So the Lowrank structure or the macroscopic quantities is encoded in the fluid limit. Now how do we utilize this Lowrank structure? Depending on if you're in the forward setting and inverse setting. If you're in the forward setting, you get good news, and in the inverse setting, you get bad news. Let me start with inverse. The rule of thumb is if the forward problem is a good problem, then the inverse problem is a bad problem. So good problem means you have a little bit perturbation in your initial data and you put it in your system. After all, you don't have many perturbation in your final solution. But in the inverse setting, if you have 2 different initial conditions that gives you the same final data, the basically means tracing back to your initial data is very hard. So in this sense, good forward problem means lots of degrees of freedom do not matter. You can throw away all the details, but in the inverse setting, you do need those details to reconstruct your parameters. So in our case, let's come back to the radiative transfer equation and the diffusion equation. Radiative transfer equation means your Newton number, roughly speaking, is order 1. And the diffusion equation means your Newton number is extremely small, and you have the comparison between the laser light and the flashlight. Now imagine you have this light source, and you want to shine it to my hand, and I want to take a picture of my hand. If you use a high energy photon, X-ray, you shine it over my hand, I get very sharp image. But if you have flashlight, and if you shine it on my hand, on this side you do see a little bit of light information, but it's very, very blurred image. You don't get too much of a good structure of the hand. That's what you get. So I fire photon particles to the tissue, and the photons scatter around and gradually set out and get received by the detector. If the photon particle gets sent in, it's high energy photon, in the sense that the wavelength is extremely low. We call it the X-ray or optical tomography, and one has very sharp image. Or if you shine light that has low energy, if you shine low energy photon to the tissue, in the sense that the wavelength is much longer, or in the sense you are in the near infrared structure, then the picture is much more blurred. In this sense, people call it the diffuse optical tomography, or mathematicians call it the Calderon problem. Calderon is the Argentina mathematician who firstly started this problem. One thing that I'd like to emphasize is, from mathematical side, the inverse problem for X-ray and the inverse problem for diffusion equation have been studied by two different groups, and they come up with two different results, and these two results contradict each other. So for X-ray, people proved the Lipschitz stability. I'm going to talk about Lipschitz stability later. And for inverse heat equation, people proved its logly yield, in the sense that the optical tomography, I define this operator called Albedo Operator. I shine lights in and I collect the lights out. So this maps the incoming to the outgoing data. If I perturb this map by a little bit, the reconstruction of my hand only perturbed by a little bit as well. So the reconstruction, the perturbation in my reconstruction is bounded by the perturbation in my measurement. However, for the heat equation, we use the so-called Dirichlet to Normal map. I give you the incoming data, and I measure the outgoing data. This D2N map maps incoming to the outgoing. If I perturb this map by a little bit, my reconstruction for my hand gets perturbed exponentially big. So that's why we say the Albedo operator reconstruction of the hand is Lipschitz stable, but the reconstruction of my hand for the heat equation is logly ill. So these two different communities, they arrive at two results. They are both sound, mathematically good. That puzzles me in the sense that, oh, sorry, this is the picture that we were, so I don't know the spectrum for this, the photon, the energy for the photon for this picture, but I think it's from here. So that puzzles me because I know the radiative transfer equation is basically the diffusion equation. And I can prove the albedo operator you use for the reconstruction is equivalent to the Dirichlet to normal map. However, the reconstruction is stable using albedo operator, but not stable using D2N map. And that's a contradiction. I'd like to understand why. In a nutshell, we got the following two theorems. The nonlinear, depending on if you're in the nonlinear region or in the linear region. In the nonlinear region, we carefully traced the constant in front of the perturbation. So this constant tells you by how much I'm enlarging the perturbation in my reconstruction. And we can prove this constant grows up exponentially fast when Newton number is small. If you give me a very small Newton number, this constant is extremely big. So if you're multiplying your perturbation, which can be small, by an extremely big number, that basically says your reconstruction is very bad. In the linearized setting, we basically write it in the following formula. We have the interpreter multiplying the things that you want to reconstruct equals to my data, and we can prove this interpreter is extremely small when this number is small. So if you have a very small number here, you divide it over, that means any perturbation in your data is going to be magnified by this extremely big number in your reconstruction for A. So that's the stability issue for reconstructing my media using radiative transfer. So these are some numerical simulation, and this is to demonstrate that this system is indeed Lipschitz in in the sense that I perturb my media linearly, I perturb my hand linearly, and the perturbation in my observation grows linearly with it. And this is to show that this constant indeed grows exponentially fast when your Knudsen number is small. So there are two comments that I'd like to mention. Number one is the uniqueness result is obtained by comparing radiative transfer equation with X-ray. And the linearized setting can be tricky. More specifically, so finally I'm writing down the radiative transfer equation. This is the transport term, and these two terms are for different things. This term basically says my photon gets absorbed by my media, and this absorption rate is captured by this sigma A. So you have a negative sign, meaning you get absorbed. And over here, this is called the scattering term that basically says my photons interact with the media and then get scattered. If I change this equation a little bit, just move this term to the left-hand side, I call this term A operator, and I call this term B operator. These two terms do different things. The first term says, I apply this operator on my solution, then my solution exponentially decay. The second term is the integral term. So that basically mix out everything in my neighborhood. So these two terms, this basically says I have the exponentially decaying rate, and this basically says I'm communicating with my peers. So if you can separate these two terms, then you're basically separating this, we call it the X-ray, and this includes X-ray with a multi-scattering. Nevertheless, the first term is the X-ray, and the second term is the scattering operator, and we can show that if your scattering is extremely strong, in the sense you're in the thick, optically thick region, your cloud is very thick, then you're further and further away from X-ray. X-ray is stable, and then if you're further and further away from X-ray, yes, the reconstruction is worse and worse. So in the end, we get this nonlinear theorem that the reconstruction of my media is exponentially enlarged by the perturbation in my measurement. The second comment is the linearization is tricky. So over here, I finally write it in this linear system. I have the data on the right-hand side and have some function that I can explicitly write down, and I can show it's small, and I want to reconstruct this media A. Or in the linear algebra setting, I write it as a matrix times something you want to recover equals to my data. But there are two smallness, so you need to be very, very careful. Number one thing is, for the linearization to carry out, you are assuming my media is close enough to the background media. So this is sigma is my true media, and you have some background media. I'm assuming the perturbation is extremely small. At the same time, you're also assuming the Knudsen number is small. So there are two smallness you have to compare that makes the linearization very tricky. But let's not talk about the details. In the end, this is the final result in the sense that this guy gets extremely small, so it enlarges the perturbation in the algebraical fashion. Okay, so the inverse problem becomes bad, means the forward problem should be a good one. I'd like to start with this diagram. L is a very abstract operator, and in our situation, it's a radiative transfer equation with a small Knudsen number. I apply this operator onto the solution, it equals to the source term. And we have proved that when epsilon is extremely small, the Knudsen number is extremely small, this system becomes another system, and in our case, is a diffusion equation. But let's pay a little bit attention to the dimension we are in. The radiative transfer equation, x is 3 dimension, v is the angle, that's 2 dimension. In total, it's 5 dimension. And the heat equation, however, you only have one variable x, that's 3 dimension. So you're immediately compressing your information by 2 dimensions. So apparently, numerically, it's much easier to compute the heat equation than computing right away with the radiative transfer. Okay. On the mathematical setting, you say, okay, I have this operator, so my solution lives in the space spanned by all the Green's function. Similarly, when you perform the homogenization, you also say my solution gets spanned by the Green's function. Mathematically, we prove that these two systems are equivalent in some sense. That basically means this Green's function and this Green's function, they are equivalent as well. If you conduct numerics, however, they are very different. If you conduct numerics, over here, you are paying 5 dimensions of grid point. But over here, you are paying 3 dimensions of grid point. So the number of grid point over here is much, much bigger than the dimension of grid point you are paying for your limiting system. So that basically means you are paying a lot more degrees of freedom that is needed. So somehow, if you embed this kind of understanding in your system, that could reduce the computation. In a diagram, we have the collection of all the Green's functions, and numerically, we know that we perform the discretization and we formulate a Green's matrix. This Green's matrix is extremely big, 10 to 5 degree to 10 to 5, those many degrees of freedom. It's a huge matrix. However, we also know that in the limiting system, the Green's matrix can be much more compressed. This direction and this direction should be 10 to 3 instead of 10 to 5. So your matrix can be compressed. Now the question is, we can really give you this Green's matrix. Right? Usually we say, I gave you a huge matrix, and I know the information can be compressed into a small matrix. That requires you to give me the huge matrix first. But in our situation, I cannot really give you this Green's matrix first. It requires you to calculate all the Green's function first. But what we can do is to prepare some realizations of it, in the sense that we populate this Green's matrix, act on some random vectors a couple of times that immediately capture the solutions, the Green's function space somehow. So let me quickly go over it. This is one of the leading algorithms in compressed sensing in recent years called Randomized SBT. It says the following. I have a matrix that is extremely big, but I know ahead of time that this matrix has a low rank structure in the sense that I can compress this matrix. I can compress it in the sense that I can find a skinny matrix Q so that this matrix projected on this Q is almost the same as this A. So geometric interpretation is I have this unit sphere and I map it to an ellipsoid. I only care about the direction gets stretched. This direction gets compressed. I can simply eliminate them. I ignore all of them. So this randomized SBT basically says you do not need to tell me the entire information of A. I just randomly find some random vectors in this unit sphere and match it to the range. The span of the result is going to generate you the whole range. So in some sense, if your matrix is rank K, for example, if this ellipsoid, roughly speaking, approximately have 5 directions get stretched, then you only give me 5 random vectors. I apply my matrix on these 5 vectors. The solution already generates the entire range of the matrix. So it's a randomized version of an algorithm. So the theorem is also a randomized version of it. You gave me a random matrix. I I map this matrix onto this random matrix, perform the QR factorization, etc. And I say that the range that you accumulate, this cube, largely preserves the information. So that was the core of the algorithm that we prepared. We gave you this, we do not know this G, but I can prepare several realizations of this G by multiplying this G with some random vectors. So offline, I prepare you some solution space, and I basically say my solution lives in this solution space spanned by this approximation. So let's not worry about that. There are some simulations for radiative transfer equation with Henry-Greenstein model. With different epsilon, you can see the singular value decays with different fashion, and smaller epsilon gives you the faster decay. And these two are the reference solution. So I basically construct this entire Green's matrix, and I ask what are the first two leading singular vectors that are produced in this Green's matrix. These are the reference solution, and these two are the randomized version of this algorithm. You can basically see no difference between them. But if you zoom in, you probably see a little bit perturbation over here and over here. That's because you're using the randomized version of the algorithm. And in the end, when epsilon is 1, so when you do not have the the smallness in your Knudsen number, the simulation is bad. But when your Knudsen number is small, now over here is, I think it's a 15% of compression rate. This is 30% of the compression rate. The error looks like the following. When epsilon is 2 to minus 4, which is mediocre small, with 8% of the basis functions, suppose you want to use 100 grid point initially, now I only use 8 grid point, my error is already down below 2%. This is another example. I have two small variables over here. For epsilon equals to 1, I do not have good capturing. But for epsilon equals to 1 over 36, I have different compression rate. Let's see the error. So with 15% of the grade point, so you pay 100 grade point initially, now I pay 15 grade point. I roughly capture the behavior, and with 35% of the grade point, I basically capture the entire solution space. So let's say, this one. Let me quickly wrap up. So in this talk, I talked about the Lowrank structure in forward setting and the inward setting of kinetic equation. My kinetic equation, roughly speaking, can be classified into this one. And in the forward setting, I'm saying this equation can be homogenized. You have this small parameter to tune, and when it is small, you can compress your information. You can delete lots of degrees of freedom that advances your computation using the random fashion. And in the inverse setting, I use the Lowrank structure to explain the ill-posedness. I basically said when your Knudsen number is extremely small, your system is ill, and you cannot reconstruct the parameters in your equation. With that, I think I'm ready to wrap up. Yeah, thank you.
We have time for a few questions. Okay, so if I understood one element of what you were talking about, there's the question of how many degrees of freedom are actually meaningful for the problem.
That's right, yes.
And so the example that comes to my mind is if you have a cloud that has a lot of internal three-dimensional structure,
Yeah.
a lot of that structure doesn't actually matter in the end. You
Yes.
can do the forward calculation, you can find your results for the reflected radiation, the diffuse radiation, but you can change things around that cloud quite a bit, and you'll get the same basic answer
Yeah.
back out. Is
Yeah.
there a formalism for going back and saying, or trying to identify from your system how many degrees of freedom are actually needed to adequately characterize?
Mathematically, I think it's a very hard problem. numerically, I think it's going to be just be answered by the singular value. So you prepare your entire Green's function space, and you plot out your singular value decay. Usually it's exponentially decay, and you basically say, suppose I tolerate 10% of error, then how many singular values I'm keeping, and how many singular values I'm throwing away. But mathematically, I think it's a very hard question. But yeah. It's similar to the homogenization problem you were asking earlier.
All right.
Yeah.
Any other questions?
So, in this case of finding the sparse structure, do you not have, so you don't have to actually sit down with paper and pencil and work through it, right? So if I have just a code with all of this set up, then all I need to do is be able to generate the matrix and work with it. So I don't have to try to work on anything analytically?
That's right. That's the beauty of this algorithm. So there's many things that I'm deleting in the end. So this is a homogenization for elliptic equation. I don't think it's studied too much in this building, but mathematically we think it's a very important problem. Over here we have a small number over here, and the media is highly oscillatory. So analytically, people's view for 2 decades was, can I derive the effective media that replaces things by some homogenized media? And that requires lots of analytical understanding. And based on that analytical understanding, there are tons of work, numerical work, based on that analytical understanding. And our point of view is, we do not have this analytical understanding. Can we use some random sampling to immediately and directly capture your Green's function space? And the answer is we can.
Okay.
Yeah.
So I have another question, which is really more about terminology. One of the things that I learned in our conversation earlier is that often we're talking about a lot of the same kinds of things, but the terminology in different communities can be quite different.
Yeah, that's right.
And so when you talk, for example, about the rank of the matrix
Yeah.
and how you can compress matrices,
Yeah.
is that the same as finding the eigenvalues and eigenvectors in the matrix and throwing away the components that have small eigenvalues? So basically finding the underlying dimensionality of the problem
That's
by
right.
discarding the lower, the smaller eigenvalues and their corresponding eigenvectors.
Yeah. The singular value and eigenvalue are equivalent to your matrix asymmetric. In our case, we can tolerate asymmetric matrix as well, but the idea is the same.
Thank you.
Yeah. I should have made that more explicit.
Any other questions? Well, thank you again for a very interesting talk.
Thank you.